Most people imagine a black hole as a kind of cosmic vacuum cleaner, a violent object that drags everything nearby into darkness. But that picture is wrong. A black hole is not a mouth. It does not reach out. It does not hunt. At its edge lies something far more subtle, a boundary called the event horizon. The event horizon is not a physical surface. It is not a wall or a doorway, or a point of no return in the dramatic sense. It is a line in space-time where familiar ideas quietly begin to change. Beyond this boundary, escape no longer means what it used to mean. Direction becomes ambiguous, and even the idea of the future starts to behave differently. Tonight, we're not here to rush toward that boundary. We're going to approach it slowly. We'll build a black hole from the beginning, from the life and death of a massive star, through the calm, inevitable collapse that follows. And only then will we ask the real question: what actually happens beyond the event horizon? No speculation, no science fiction, just a careful, calm journey guided by the best physics we have. To understand what happens beyond the event horizon, we first need to understand how a black hole is born. A massive star lives fast from the very beginning. It is born with far more material than it can ever hold gently, and so it burns its fuel quickly, intensely, and without hesitation. Where smaller stars can shine for billions of years, a massive star races through its life in a fraction of that time. At its core, the process is simple. Hydrogen fuses into helium. Helium fuses into carbon. Carbon gives way to heavier elements, one layer at a time. Like the rings of an onion, the star builds itself inward, each shell producing energy, each reaction pushing outward against gravity. For most of the star's life, this balance holds. Gravity pulls inward. Energy from fusion pushes back. But that balance has a limit. Eventually, the star begins to create iron, and iron changes everything. Unlike earlier elements, iron does not release energy when it fuses. Instead, it consumes energy. It offers no outward pressure in return. This is the quiet end of the star's productive life. Not with a bang, but with a failure. Once the core fills with iron, the star has no new source of support. Fusion stops helping. The outward pressure fades. Gravity, patient and relentless, takes over. The core collapses. In a fraction of a second, electrons are forced into protons, combining to form neutrons. In the process, an enormous flood of neutrinos escapes, carrying energy away almost instantly. The collapse halts abruptly, and the outer layers of the star rebound. This rebound is what we see as a supernova, not an explosion caused by excess energy, but a violent reaction to sudden collapse. The star's outer layers slamming outward after losing their support. In that brief moment, the universe is enriched. Elements heavier than iron are scattered into space, the raw materials that will one day become planets, oceans, and the atoms inside your own body. What remains at the center is something extraordinary. A neutron star, roughly the size of a city, yet more massive than the sun. It is one of the densest objects the universe can produce, without becoming something else entirely. This is not a black hole. Not yet. It is a star held up by forces far stranger than heat or pressure. Forces rooted in quantum physics itself. And it is balanced on the edge of a final decision. What's left behind is not a black hole yet, but something even stranger. A neutron star may look simple from the outside. It appears small, dense, quiet, but it is not a solid ball in the way we usually imagine matter. A neutron star is not held up by heat. It is not held up by pressure from burning fuel. And it is not rigid in the ordinary sense. It survives collapse for a very different reason. A neutron star is a quantum object. That idea can sound intimidating, but the underlying principle is surprisingly gentle. At the most basic level, matter is made of particles. Some of those particles belong to a family called fermions. Neutrons are fermions, electrons are fermions, and fermions obey a simple rule known as the Pauli exclusion principle. In plain terms, this rule says that two identical fermions cannot occupy the same quantum state at the same time. They can be close, they can be packed tightly, but they cannot be perfectly stacked on top of one another. To understand why this matters, it helps to change how we picture space. In everyday life, we think in 3 dimensions: left and right, forward and back, up and down. But quantum physics adds another layer. Each particle is defined not only by where it is, but also by how it is moving. Together, position and motion form what physicists call phase space, a 6-dimensional description made from 3 dimensions of position and 3 of momentum. You don't need to picture all 6 dimensions. You only need the idea that each particle needs its own unique slot. One way to imagine this is as a parking lot. Each quantum state is a parking space. Each fermion needs its own space. No 2 identical fermions can park in the same one. As a neutron star collapses, its particles are squeezed closer and closer together. The parking spaces fill up. When all the low-energy spaces are taken, additional neutrons are forced into higher energy states. They are not moving faster because they want to. They are moving faster because they have no choice. This creates a powerful resistance to further compression. That resistance is called degeneracy pressure. Unlike ordinary pressure, degeneracy pressure does not come from heat. It does not depend on temperature. It does not fade as the star cools. It is a purely quantum effect, a consequence of the fact that matter cannot be packed arbitrarily tightly. In a neutron star, this pressure is immense. It is strong enough to hold up an object more massive than the Sun, compressed into a sphere only a few kilometers across. This is why collapse does not immediately continue. Gravity pulls inward without pause. But quantum mechanics pushes back, silently and relentlessly. For a time, the 2 forces reach a fragile balance. The star does not explode, it does not expand. It simply exists, suspended between opposing rules of nature. This balance is not guaranteed forever, but it is real. And it is one of the clearest demonstrations that quantum physics is not confined to tiny scales. Here, the same principles that govern electrons in atoms are holding up an entire star. A neutron star is matter at its limit, supported not by fire, but by the quiet refusal of quantum states to overlap. For now, collapse has been stopped, but gravity has not given up. It is waiting. But gravity has one final move left. For a time, quantum pressure holds the line. The neutron star exists in a delicate balance. Gravity pulling inward, quantum mechanics pushing back. But gravity does not need to push harder. It only needs to change the rules of the space in which the struggle takes place. Gravity, in Einstein's description, is not a force in the usual sense. It is geometry. Mass bends space-time. And as mass increases, that curvature deepens. As a neutron star gains more mass, from infalling material or from merging with another dense object, something subtle begins to happen. The star's radius shrinks. This much is expected. More mass means stronger gravity, and stronger gravity compresses matter further. But at the same time, something else is growing. The radius of the event horizon. The event horizon is not a surface you can touch. It is a geometric boundary, a region where space-time is curved so steeply that all possible paths point inward. As mass increases, this boundary expands outward. So now there are 2 curves moving in opposite directions. The physical size of the neutron star is getting smaller. The size of the event horizon is getting larger. These two curves are not aware of one another. They do not collide. They do not interact. They simply move. And then, at a precise point set by the geometry of space-time, they cross. There is no explosion. There is no flash of light. There is no sound. Nothing dramatic announces the moment. The neutron star does not tear itself apart. It does not suddenly collapse faster. Instead, it quietly passes a threshold. The moment the entire star fits within its own event horizon, the story changes. From the outside, there is no longer a visible surface. There is no longer a boundary where matter ends and space begins. There is only a region from which information cannot escape. This is the birth of a black hole. Not as an object that forms in an instant, but as a consequence of geometry reaching a critical configuration. Quantum pressure has not failed in the way we usually imagine failure. It has not weakened. It has not vanished. Inside the event horizon, quantum effects may still exist. Neutrons still obey the Pauli exclusion principle. Particles still resist being packed too tightly. But once the horizon forms, resistance no longer matters to the outside universe. What happens next cannot influence anything beyond that boundary. This is why a black hole does not need to crush matter into nothingness. It does not need infinite force. It does not need violence. It only needs space-time to curve enough that all futures lead inward. From this point on, collapse is no longer something that can be stopped, because stopping would require sending information outward. And outward paths no longer exist. There is no last signal, no final warning. The neutron star does not announce its transformation. It simply becomes hidden. What remains accessible to the universe is not a material object, but a region defined by mass, spin, and charge. A simplified imprint of everything that fell inside. The transition from neutron star to black hole is not a crash. It is a crossing, a quiet change in geometry, where the balance between gravity and quantum mechanics gives way not because quantum rules were broken, but because space-time itself was reshaped. From the outside, nothing escapes. From the inside, the future narrows to a single direction. And with that, a new kind of object has entered the universe. From this moment on, escape is no longer part of the story. The neutron star has crossed its last stable balance. Quantum pressure still exists. The rules of particle physics have not disappeared. But the geometry of space-time has changed enough that those rules can no longer protect the outside universe from what comes next. This is the moment a black hole forms. It does not begin with an explosion. It does not announce itself with light or sound. There is no sudden flash, no tearing apart of matter. Instead, a boundary quietly appears. The event horizon. The event horizon is not a shell, and it is not a surface you could touch. It is not made of matter. It is not a wall. It is a causal boundary. At this boundary, space-time is curved so steeply that every possible path forward points inward. Not inward in the sense of falling faster, but inward in the sense that all futures now lead the same way. This is why familiar ideas begin to fail. Outside the horizon, we can talk about escape velocity, how fast something must move to break free. At the event horizon, that concept stops being useful. There is no speed that leads outward anymore. Even light, which always moves as fast as the universe allows, finds no path that escapes. This does not happen because gravity suddenly becomes violent. It happens because the shape of space-time no longer offers an exit. And there is something else that quietly disappears at this moment. The surface. A neutron star, dense as it is, still has a surface. There is a place where matter ends and space begins. In principle, something could strike it. A black hole has no such boundary. Once the event horizon forms, there is no physical surface left for the universe to interact with. No solid layer, no edge to collide with. Matter does not pile up at the horizon. It does not stack or harden or freeze into a shell. From the outside, the details of what crosses the horizon fade away, not because they are destroyed, but because they are no longer accessible. This is where black holes differ most clearly from ordinary objects. For an observer far away, a newly formed black hole can be completely described by just three properties: its mass, its spin, and its electric charge. This idea is known as the no-hair principle. It does not mean black holes are simple on the inside. It means that everything complicated about the material that formed them is hidden behind the horizon. The precise composition of the star, the arrangement of its particles, the complex structure that once defined it, all of that becomes unreachable. What remains visible to the universe is not a star, but a region of space-time defined by geometry. This is why a black hole should not be thought of as an object in the usual sense. It is not a thing sitting in space. It is a condition that space itself has entered. A region where the future is constrained, where paths narrow, and where information cannot return. This shift can feel unsettling, but it is also deeply logical. Nothing violent has occurred. No law of physics has been broken. The universe has simply followed its own rules to their natural conclusion. Once the event horizon forms, the outcome is no longer uncertain. The black hole does not swallow what comes next. It does not need to. It reshapes what next even means. From the outside, time stretches. Signals slow, information fades. From the inside, every possible future points deeper inward. This is not a catastrophe. It is a transition, a moment where matter gives way to geometry, where an object becomes a region, and where the universe quietly accepts a new boundary it cannot look past. The black hole has formed. And yet, this is not the only way such boundaries may come into existence. But black holes may not all be born from dying stars. When we think about black holes, we usually imagine endings: dying stars, collapsed cores, the final moments of something once bright. But the universe may have found another way to make black holes, long before the first star ever ignited. To see how, we have to go back to the very beginning. In its earliest moments, the universe was extremely hot, extremely dense. Everything we see today was once packed into a space far smaller than we can easily imagine. At first glance, it might sound like the perfect place for black holes to form. But density alone is not enough. The early universe was not a smooth, uniform soup. It was slightly uneven. Tiny variations in density, called density fluctuations, were present from the start. Some regions were a little denser, others a little thinner. These differences were small, but in a universe this young and compressed, small differences mattered. Still, even this was not sufficient. The universe was also expanding rapidly. Expansion acts like a kind of stretching force, pulling matter apart and preventing it from collapsing too easily. So for a black hole to form in the early universe, a region had to meet two conditions at once. It had to be denser than its surroundings, and dense enough to overcome the universe's rapid expansion. Radiation pressure also played a role. In the early universe, radiation was not just light. It carried energy and pressure, pushing outward and resisting collapse. Only regions where gravity could overpower both expansion and radiation pressure had a chance to collapse completely. If such a region crossed that threshold, it could form a black hole directly, without the need for a star. These hypothetical objects are known as primordial black holes. They are different from the black holes formed by stellar collapse. Primordial black holes could span an enormous range of sizes. Some might have been incredibly small, with masses comparable to a mountain. Others could have been as massive as stars or even larger. Their size depended entirely on when they formed and how large the collapsing region was at that moment. What matters most is that this idea is not science fiction. Primordial black holes arise naturally from well-established physics. They appear in serious cosmological models, and they are studied using real observational data. Physicists look for their effects rather than their light. Because black holes do not shine, the only way to find them is through gravity. If primordial black holes exist, they would bend light as they pass in front of distant stars. They would influence the motion of galaxies. They would leave subtle fingerprints in the large-scale structure of the universe. So far, observations have placed strong limits on how many primordial black holes can exist and how massive they might be. Some possibilities have already been ruled out. Others remain open. This is how the idea stays grounded. It survives not because it is dramatic, but because it can be tested. If primordial black holes formed in the early universe, they would be among the oldest objects that exist. Older than stars, older than galaxies, older than planets. They would be fossils from a time when the universe itself was still taking shape. And if they are still around today, they may still be quietly influencing the cosmos, shaping the motion of matter through gravity alone. This possibility opens a new chapter in the story, because once black holes appear in the early universe, they begin to overlap with another deep mystery, one that has nothing to do with light and everything to do with what we cannot see. If primordial black holes exist, they might still be shaping the universe today. Dark matter enters astronomy quietly. We do not see it, we do not touch it, but we know it is there. Galaxies rotate too fast for the matter we can observe. Clusters of galaxies hold together more tightly than visible mass allows. Light bends around empty-looking regions of space. Something unseen is adding gravity. This unseen component is what we call dark matter. It does not glow. It does not emit light. And as far as we can tell, it barely interacts with ordinary matter at all. That description immediately made primordial black holes an attractive candidate. Black holes are dark. They interact almost entirely through gravity. And if they formed early enough, there could be many of them spread throughout the universe. For a time, the idea was taken very seriously. If primordial black holes made up dark matter, they would not announce themselves with radiation. They would reveal themselves only through subtle gravitational effects. So scientists went looking for those effects. One of the first tests involved gravitational microlensing. When a massive object passes in front of a distant star, its gravity slightly bends the star's light, causing the star to briefly brighten. If primordial black holes were common in certain mass ranges, astronomers would see many of these brief, brightening events. They did not. Large surveys monitored millions of stars for years and found far fewer microlensing events than required. That ruled out primordial black holes in several mass ranges. Other tests followed. Primordial black holes passing near binary star systems would disrupt their orbits over time. Those disruptions were not observed. In dense environments, black holes passing through neutron stars could be captured and destroy them from the inside. The continued existence of old neutron stars placed strong limits on how many primordial black holes could exist. Bit by bit, the allowed possibilities narrowed. Many mass ranges were excluded entirely. Others were constrained so tightly that primordial black holes could make up only a small fraction of dark matter. Today, only a few narrow windows remain open. Specific mass ranges where primordial black holes have not yet been ruled out. Even those windows are shrinking as observations improve. This is not a failure of the idea. It is how science works. Hypotheses are not protected. They are tested. And when evidence disagrees, the universe is allowed to say no. Primordial black holes may still exist. They may still contribute to dark matter in limited ways. But the evidence strongly suggests they are not the primary answer to the dark matter problem. This leaves us with something important. Dark matter remains unidentified. It is still shaping galaxies, still influencing the large-scale structure of the universe, still pulling quietly on everything we can see, and yet, it is probably not made of black holes. This realization changes the role primordial black holes play in the story. They move from being a possible solution to being a reminder. A reminder that gravity alone does not always explain everything. A reminder that nature is not obligated to choose the simplest idea we prefer. And a reminder that black holes themselves still contain mysteries deeper than their connection to dark matter. To understand those mysteries, we need to turn inward, away from what black holes might be made of, and toward what lies at their very center. To understand the deepest mystery of black holes, we need to talk about singularities. The word singularity carries a lot of weight. It sounds final, mysterious, almost threatening. But in physics, a singularity is not a place you can visit, and it is not a thing waiting at the center of a black hole. It is a signal. To see why, it helps to step back. In classical physics, even long before Einstein, singularities already appeared. In Newton's law of gravity, the force between two masses grows stronger as they get closer together. As the distance approaches zero, the force grows without bound. Mathematically, it becomes infinite. But no one takes that infinity literally. It simply tells us that Newton's equation was never meant to describe what happens at zero distance. The model breaks down. Einstein's general relativity brought a deeper understanding of gravity, but it did not eliminate singularities. It refined them. In general relativity, we must be careful to distinguish between two very different ideas. A coordinate singularity is one that comes from how we describe space-time, not from space-time itself. A classic example is the event horizon. In some coordinate systems, the equations appear to blow up at the horizon. But this is an illusion of the math. Change the coordinates, and the apparent singularity disappears. Nothing physical is happening there. A physical singularity is different. It appears when measurable quantities, such as density or curvature, grow without bound, no matter how the equations are written. In the simplest description of a black hole, this happens at the center. But here is the crucial point. An infinite value in physics almost always means we have pushed a theory beyond the domain where it applies. It does not automatically mean the universe itself contains infinities. In fact, infinities are usually a warning sign. They are nature's way of saying, your current tools are no longer adequate. One useful way to think about a singularity is as an error message. When a computer encounters a situation it cannot handle, it does not reveal a deeper truth, it stops. The output tells you not what reality is, but where your model has failed. Singularities play a similar role in physics. General relativity is an extraordinarily successful theory. It has passed every test we have thrown at it. But it does not include quantum mechanics. And near the center of a black hole, both gravity and quantum effects should be important at the same time. That is precisely the regime where we expect our current theories to struggle. This is why it is important to separate the event horizon from the singularity. The event horizon is a real geometric boundary. It has clear physical meaning. It affects what signals can escape and what cannot. The singularity, by contrast, marks the edge of what our equations can describe. It is not necessarily a location in space. It is not necessarily a point in time. It is a statement about limits. This perspective changes how we think about black holes. Instead of imagining a tiny, infinitely dense object hidden inside, we can think of a region where our best descriptions stop working. The mystery is not that the universe becomes impossible. The mystery is that our theories are incomplete. And that realization should feel calming rather than alarming. Physics has encountered limits before. Each time, those limits led to deeper understanding, not to the end of explanation. Singularities remind us that black holes are not places where science fails, but places where science has more to learn. They mark the boundary between what we know and what we are still working toward. To move forward, we do not need to imagine anything exotic or speculative. We only need to look more carefully at how space and time behave as gravity bends them to their extremes. Because before we can talk about what lies beyond our theories, we need to understand what happens at the boundary we can still describe. To see why singularities feel so strange, we have to look at how space and time behave near the event horizon. Before we talk about what happens inside a black hole, we need to pause and talk about something more familiar: cause and effect. Every experience you have ever had fits into a simple structure. Something happens, and then something follows. This order is not a habit of the mind. It is built into space-time itself. In physics, this order is described using world lines. A world line is the path an object traces through space-time, not just where it goes, but when it goes there. If you imagine space-time as a map, a world line is the line that represents your life. From birth, through every moment you move forward in time. No matter how fast or slow you travel, no matter how differently two observers move, everyone agrees on one thing. Events along your world line happen in a fixed order. This order is measured using something called proper time. Proper time is simply the time measured by a clock moving with you. It is the time your body experiences, your own ticking seconds. Different observers may disagree about distances. They may disagree about how long an event appears to last. But they will always agree on what comes before and what comes after along a single world line. This agreement is protected by the structure of space-time. At the heart of that structure is the space-time interval. Without using equations, the idea is this: space-time has a built-in rule that separates events into categories. Some events can influence each other. Some cannot. If one event can cause another, then every observer agrees on their order. This is why causality feels so stable. The future is not just something we expect. It is a direction. Much like north or south, the future is a direction that space-time itself defines. You can slow down how quickly you move through time. You can speed it up relative to someone else. But you cannot reverse direction. This is not because physics forbids strange ideas. It is because the geometry of space-time makes them unnecessary. Inside this structure, cause always comes before effect. Nowhere in ordinary space-time can you step sideways into yesterday. Nowhere can you turn around and walk into your own past. This consistency is what allows the universe to function. Stars form, atoms interact, life unfolds. Black holes do not break this structure. That point is important. They do not tear causality apart. They do not create paradoxes. They do not allow effects to happen without causes. Instead, they reshape how the structure is experienced. Outside a black hole, the future points forward in a familiar way. Inside, something subtler happens. The rules of causality remain intact, but the roles played by space and time begin to change. This does not mean chaos, it means constraint. Just as space-time defines a future direction for every observer, it also defines which paths are possible and which are not. Near a black hole, those paths narrow. The freedom to choose a direction through space gradually disappears. This narrowing does not happen suddenly. It does not announce itself. It emerges naturally from the same geometry that keeps cause and effect in order everywhere else. This is why black holes are so powerful as teaching tools. They do not introduce new rules. They expose the ones we already rely on. They show us that causality is not an abstract idea, but a physical structure, one that can bend, stretch, and tilt without ever breaking. To understand what lies beyond the event horizon, we do not need to abandon logic. We need to follow it more carefully, because inside a black hole, the future still exists. It simply points somewhere unexpected. Inside a black hole, the direction of time itself may take on a very different role. Outside a black hole, time behaves the way we expect. Moments follow moments. Causes come before effects. The future lies ahead, and the past stays behind. No matter how fast you move or where you go, that direction never changes. But the event horizon marks a boundary where the structure of space-time itself rearranges. Not violently, not suddenly, but completely. To understand what happens inside, we need to be careful about one thing. This is not about what you feel. It is about what the mathematics of space-time tells us must happen to every possible path forward. In ordinary space, you can choose a direction. You can go north or south, left or right, toward something or away from it. Time is different. You do not choose tomorrow. You arrive there. Outside the event horizon, space gives you options. Time gives you only one. Inside a black hole, those roles begin to swap. In the mathematical description of space-time near a black hole, the coordinate we normally call radius, the distance from the center, changes its character. It becomes time-like. That word sounds abstract, but its meaning is surprisingly simple. A time-like direction is one you must move along, just as you must move forward in time. Once inside the event horizon, moving inward is no longer a choice. It is not something you do. It is something that happens. Just as you cannot stop time from passing, you cannot stop your distance from the center from decreasing. This does not mean you feel pulled. There is no sudden force, no crushing pressure at the horizon itself. In ideal conditions, crossing the event horizon feels unremarkable. No alarm sounds. No wall is struck. No shock announces the transition. Locally, the laws of physics remain the same. But globally, the structure has changed. Inside the horizon, there is no path that leads back outward. Not because you lack speed, but because outward is no longer a direction toward the future. All future-directed paths lead deeper in. This is why escape becomes impossible. It is not forbidden by force. It is forbidden by geometry. Now we can return to the idea of the singularity. In popular descriptions, the singularity is often imagined as a place, a tiny point in space where everything piles up. That image is misleading. Inside a black hole, the singularity behaves less like a location and more like an event. It is not something you can avoid by steering differently, because there are no alternative directions left. It lies in the future of every possible world line. Just as tomorrow comes whether you run or stand still. The singularity comes not because you fall toward it, but because time carries you there. This reframing matters. It removes the idea of violence. Nothing inside the black hole is being dragged screaming toward a point. Instead, the structure of space-time has narrowed the future until only one outcome remains. This does not break causality. Causes still come before effects. World lines remain continuous. Proper time still ticks forward for anything crossing the horizon. What changes is not logic, but freedom. Outside the horizon, you can choose where to go in space. Inside, space has lost that role. The future has taken over. And this is why black holes are not chaotic places. They are constrained places. They do not allow paradoxes. They do not allow shortcuts. They enforce order more strictly than almost anywhere else in the universe. Every path ends the same way, not because the universe is cruel, but because geometry has become absolute. This is also why the singularity should not be imagined as a monster waiting in the dark. It is better understood as the endpoint of description, the place where our ability to track world lines runs out. Whether anything truly exists, there is a question our current theories cannot answer. And that is an important distinction. The black hole does not tell us that reality becomes impossible. It tells us that our map ends. Up to the event horizon, we can describe space-time with confidence. Inside, we can still follow the logic of cause and effect. But beyond a certain point, our equations stop making predictions we can trust. This is not something to fear. It is something to recognize. Black holes are not places where physics breaks. They are places where physics becomes honest about its limits. And once we accept that, we can begin to ask a deeper question. If time itself can change its role so completely, what else about black holes might depend on how we describe time? Some of the strangest ideas about black holes come from asking a simple question. What if time itself were reversed? After spending time inside a black hole, it can be helpful to step back and look at the equations from a different angle. Not to speculate wildly, but to see what the mathematics quietly allows. When physicists study black holes, they sometimes ask a simple question. What happens if we reverse the direction of time? When that question is applied to the equations of general relativity, something unexpected appears. A white hole. A white hole is not a new invention. It is not added by hand. It emerges naturally as a time-reversed solution to the same equations that describe a black hole. If a black hole is a region where nothing can escape, a white hole is the mirror image. Nothing can enter. Matter, light, and information can come out, but nothing from the outside can cross inward. This contrast is clean and precise. Black hole, no escape. White hole, no entry. In the extended mathematical description of space-time, especially in the full Schwarzschild solution, white holes appear as regions connected to black holes through a larger geometric structure. In this picture, a white hole is associated with a kind of past horizon, just as a black hole is associated with a future horizon. But here's the important part. This does not mean white holes exist in our universe. It means the equations allow them. And that difference matters. To understand why white holes are so difficult to realize physically, we need to talk about entropy. Entropy is often described as disorder, but a better way to think about it is as the number of possible ways a system can be arranged. In everyday life, entropy increases. Ice melts, heat spreads out. Broken objects do not spontaneously reassemble. This tendency defines the arrow of time. The future is the direction in which entropy increases. A white hole would require the opposite. For a white hole to exist in a physical sense, matter would have to emerge in an extremely organized way, with entropy decreasing rather than increasing. That is not just unlikely, it is profoundly unstable. The smallest disturbance, a stray particle, a tiny fluctuation, would destroy the conditions needed for a white hole to persist. This is why white holes are considered physically implausible, not forbidden by mathematics, but incompatible with the thermodynamic behavior of our universe. And yet, they remain important. White holes serve as a kind of contrast agent. By imagining a region where nothing can enter, we sharpen our understanding of why black holes behave as they do. They help clarify the role of horizons. They highlight the connection between causality and time. They show us that the arrow of time is not optional. It is foundational. White holes also remind us of something subtle. The equations of physics are often time-symmetric. They do not prefer past over future. It is the state of the universe, its entropy, that breaks that symmetry. So when white holes fail to appear in reality, it is not because the equations are wrong. It is because the universe has chosen a direction. This distinction helps ground our understanding. White holes are not lurking somewhere unseen. They are not hidden gateways. They are not waiting to erupt. They are tools. They allow physicists to test ideas about horizons, about information flow, and about the deep relationship between time and geometry. In that role, they are extremely valuable. By studying why white holes do not naturally form, we learn more about why black holes do. And by understanding the limits imposed by entropy, we see more clearly how time shapes every physical process. This perspective brings us back to black holes themselves. If time, entropy, and quantum effects all play a role, then even a black hole may not be as simple as a perfectly sealed container. The horizon may still define what escapes today, but over longer timescales, the story becomes more subtle. To follow that story, we need to introduce one final ingredient: quantum physics. Because once quantum effects are included, the boundary of a black hole may not be quite as absolute as it first appears. If time and quantum physics are involved, even black holes may not be completely sealed off from the universe. For a long time, black holes were thought to be eternal. Once formed, they would simply remain, silent, dark, and unchanged forever. Nothing escaped, nothing faded, nothing evolved. This picture fit comfortably within classical physics, but it did not survive contact with quantum theory. In the 1970s, Stephen Hawking noticed something subtle. Quantum physics does not live inside space-time. It lives on space-time. And when space-time is curved, especially curved as strongly as it is near a black hole, quantum fields behave differently. This insight changed everything. To explain Hawking radiation, you may have heard a familiar story. Pairs of virtual particles appear near the event horizon. One falls in, the other escapes. That story is useful as a picture, but it is not what is really happening. Nothing is popping into existence at a single point. Nothing is being torn apart at the horizon. The true idea is quieter and deeper. In quantum physics, what counts as a particle depends on the observer. An observer far away from a black hole does not describe the vacuum the same way an observer falling freely does. Both descriptions are valid. Neither is more real than the other. Near a black hole, this difference matters. To a distant observer, the curved space-time around the event horizon changes how quantum fields are organized. Modes of the field that look empty far away do not look empty when traced back toward the horizon. The result is that the distant observer detects radiation, not because the black hole is emitting particles from a surface, but because the definition of nothing is no longer the same everywhere. This radiation is what we call Hawking radiation. It is not localized at a point, and it does not come from the singularity, and it does not require violent processes at the horizon. It is a global effect, a consequence of combining quantum fields with curved space-time. Now comes the surprising part. From the point of view of a distant observer, a black hole has a temperature. That temperature is extremely low for large black holes, far colder than the cosmic background radiation around them. But it is not zero, and anything with a temperature must radiate energy, slowly, quietly, relentlessly. From far away, the black hole appears to lose mass over time, not suddenly, not dramatically, but gradually. Now compare this with the experience of someone falling in. For that observer, Nothing special happens at the horizon. There is no burst of radiation, no wall of energy, no sudden heating. Local physics remains calm. This difference is not a contradiction. It reflects a core lesson of modern physics. There is no single, absolute description that all observers must agree on. Reality depends on how you measure it. Hawking radiation does not mean the horizon is a glowing surface. It means that the universe does not allow perfect isolation when quantum effects are included. Black holes are not completely sealed off. Over very long timescales, they change. If nothing else falls in, they slowly shrink. Eventually, unimaginably far in the future, a black hole could evaporate entirely. This idea alone was revolutionary. It told us that black holes are not eternal prisons. They are part of the universe's ongoing evolution. But it also introduced a problem, a deep one. If a black hole forms from ordinary matter that carries information, and then evaporates away through Hawking radiation, what happens to that information? The radiation looks almost perfectly thermal. It appears to carry no memory of what fell in. This is not just a philosophical puzzle. In quantum physics, information is not supposed to disappear, ever. So now we face a tension. General relativity says black holes form horizons that hide information. Quantum mechanics says information is preserved. Hawking radiation connects the two and exposes the conflict. Black holes are no longer simple endpoints. They have become laboratories, places where our deepest theories push against each other. And once black holes can evaporate, once they can change and fade, a much harder question appears. Not about temperature, not about radiation, but about the fate of information itself. Once black holes can evaporate, a deeper problem appears. Once Hawking radiation enters the picture, black holes are no longer timeless objects. They begin to change, very slowly, almost imperceptibly, but inevitably. The key idea is simple. A black hole has a temperature, and that temperature depends on its mass. The more massive the black hole, the colder it is. The less massive the black hole, the hotter it becomes. This relationship is the opposite of what we are used to. A large black hole, one formed from a massive star, is colder than almost anything else in the universe. Its temperature is far below the glow of the cosmic microwave background. For now, it absorbs more energy than it emits. So it grows. But this will not always be true. As the universe continues to expand and cool, the background radiation will thin out. Eventually, there will come a time when even the coldest black holes are warmer than their surroundings. From that moment on, they will begin to lose mass. For stellar mass black holes, this process is unimaginably slow. The evaporation time is not measured in millions of years or billions of years. It is measured in numbers so large they are difficult to speak aloud. A black hole with the mass of our sun would take far longer than the current age of the universe to evaporate completely. Far longer than galaxies will remain recognizable. Far longer than stars like the sun will continue to shine. This is why Hawking radiation does not matter for the black holes we observe today. It is not dramatic. It does not reshape galaxies. It does not create bursts of light. It is a whisper, spread across deep time. Smaller black holes behave differently. As a black hole loses mass, its temperature rises. That increase causes it to radiate faster, which causes it to lose mass even more quickly. This feedback means that very small black holes would evaporate much faster than large ones. But even here, the process remains calm. There is no explosion. There is no sudden disappearance. The black hole does not tear itself apart in a final flash of energy. It simply fades. Energy leaks away. Mass decreases. The horizon shrinks. The universe does not rush this process. It allows it to unfold patiently over timescales far beyond ordinary experience. This patience is important. Black hole evaporation does not introduce chaos. It introduces continuity. A black hole forms from matter. It exists for a long time, and eventually, it gives its energy back to the universe. In that sense, black holes participate in the same cosmic cycle as everything else. Nothing is exempt from time. Not stars, not galaxies, not even the darkest objects we know. This realization changes the emotional tone of black holes. They are no longer eternal prisons. They are long-lived, but temporary. And that leads us directly to a deeper issue, because evaporation forces us to ask what is being returned to the universe. The Hawking radiation emitted by a black hole looks almost perfectly thermal. It appears smooth, random, featureless. It does not seem to carry detailed information about the material that originally fell in. And yet, in quantum physics, information is not supposed to vanish. The evolution of a quantum system is meant to be reversible. Given enough knowledge, the past should always be recoverable in principle. Black hole evaporation seems to challenge that idea. If a black hole forms from complex matter, stars, atoms, structures, and then evaporates into simple radiation, where did the information go? This question does not arise immediately. For most of the black hole's life, the horizon still exists. Information remains hidden. The paradox only becomes sharp when the black hole is gone, when nothing remains but radiation and no horizon is left behind. This is why evaporation is so important. It is not dramatic. It is not observable today. But conceptually, it forces our theories into contact. General relativity tells us how horizons form and behave. Quantum mechanics tells us how information should evolve. Hawking radiation connects the two and exposes their disagreement. At this stage, we do not need answers. We only need to recognize the tension. Black holes are no longer silent endpoints. They are slow processes that begin with collapse and end with evaporation. And somewhere along that path, a fundamental question waits. Not about how black holes shine or how long they last, but about whether the universe allows information to be truly lost. That question is not emotional. It is structural. It goes to the heart of what physical laws mean. And it is the question that has shaped decades of debate among physicists. Once we accept that nothing lasts forever, we are ready to ask the hardest question of all. What happens to information when a black hole disappears? That is where the real mystery begins. At the foundation of modern physics, there is a rule that has never failed. In quantum mechanics, information is not allowed to disappear. It can be scrambled, it can be hidden, it can be spread across many particles, but it cannot be destroyed. This rule is not philosophical, it is mathematical. The equations of quantum physics are built so that, in principle, the past can always be reconstructed from the present if enough information is available. For decades, this principle held firm. Then black holes entered the picture. When a black hole forms, it hides information behind an event horizon. That alone is not a problem. As long as the black hole exists, the information is simply inaccessible. The real trouble begins when we combine this idea with Hawking radiation. From far away, the radiation emitted by a black hole looks thermal, random, featureless. It does not appear to carry detailed information about the matter that fell in. If a black hole evaporates completely, leaving only this radiation behind, we are forced to ask a simple question. Where did the information go? There are only a few logical possibilities. Either the information is somehow encoded in the radiation in a way we do not yet understand, or it remains hidden forever, even after the black hole is gone. or it is truly destroyed. The last option is the most troubling. If information can be destroyed, then quantum mechanics is incomplete. Its most basic rule would be violated. But if information is preserved, then something about our understanding of black holes must change. Perhaps the horizon is not as simple as we think. Perhaps space-time behaves differently at the smallest scales. Perhaps gravity and quantum theory are missing a shared framework. This is why the information paradox is not an abstract puzzle. It is a direct clash between two of the most successful theories ever developed. General relativity tells us how black holes form and hide information. Quantum mechanics tells us that information must survive. Both theories work extraordinarily well in their own domains. But here, they cannot both be right in the same way. Black holes sit precisely at that intersection. They are not exotic exceptions. They are stress tests. If our theories can be made consistent here, they can likely be made consistent everywhere. This is why the information paradox has shaped decades of serious research. Not because it is strange, but because it is unavoidable. Once black holes can evaporate, physics is forced to confront its own limits. And to move forward, it may need more than a small adjustment. It may need a fundamentally new way of thinking about space, time, and information. To resolve this paradox, physics may need an entirely new way of thinking. At this point, the tension is clear. Quantum physics tells us that information must be preserved. General relativity tells us that black holes can hide information behind horizons. Hawking radiation seems to connect the two, and in doing so, makes the conflict unavoidable. To see why this problem reaches beyond black holes, we need to introduce one more idea: entropy. Entropy is often described as disorder, but a more precise way to think about it is as a count. It measures how many microscopic arrangements can produce the same large-scale appearance. The higher the entropy, the more ways the system can be arranged. This is why entropy gives time its direction. As systems evolve, they move toward states with more possible arrangements. The arrow of time points toward increasing entropy. Black holes fit into this story in a surprising way. A black hole has entropy. In fact, it has an enormous amount of it. According to well-established results, the entropy of a black hole is proportional to the area of its event horizon, not its volume. This alone is unusual. It suggests that information is not stored inside the black hole in the way we expect, but somehow associated with its boundary. This idea quietly reshapes how we think about space-time. If entropy counts information, and if black hole entropy scales with area, then information may be woven into geometry itself. Now the deeper conflict becomes visible. Quantum mechanics insists that information is preserved in time. General relativity allows space-time to curve, stretch, and hide regions from view. Each theory works perfectly where the other is negligible. Quantum physics dominates the small. General relativity dominates the large. A black hole is where both matter at once. It is a region where tiny quantum effects are magnified by extreme gravity. And it is precisely here that our current descriptions stop aligning. This does not mean either theory is wrong. It means neither is complete on its own. What seems like a paradox may simply be a sign that we are trying to describe one reality using two partial languages. This is why physicists speak of quantum gravity, not as a finished theory, but as a direction, a framework that would describe space-time itself as a quantum object, a theory where geometry and information are not separate ideas, but different expressions of the same structure. From this perspective, the information paradox is not a dead end. It is a guidepost. It tells us where our understanding becomes thin and where new ideas are needed. Science advances this way, not by avoiding contradictions, but by taking them seriously. Black holes do not represent failure. They represent opportunity. They force our most successful theories to meet each other honestly. And in that meeting, something deeper may emerge. For now, we do not need answers. We only need clarity. We are standing at the edge of what we can describe. Not because the universe is meaningless, but because it is richer than our current tools allow. And before we let our minds wander too far into speculation, it is worth remembering something simple. We are still here, still observing, still learning. It's worth remembering where we actually are. By this point, we've traveled very far. We've followed collapsing stars, crossed event horizons, and explored the deepest limits of physics. So before we go any further, it's important to pause and clear away a common fear. Black holes are not hunters. They do not roam the universe searching for things to swallow. They do not reach out. They do not chase. In one crucial way, a black hole behaves just like any other object with mass. It follows the same laws of gravity as stars, planets, and galaxies. Nothing more, nothing less. Here is a simple way to see this. Imagine the sun were suddenly replaced by a black hole with the same mass. It sounds dramatic, but the result would be surprisingly calm. The Earth's orbit would not change. It would continue circling in exactly the same path as before. Why? Because gravity depends on mass, not on whether that mass is a star or a black hole. From far away, a black hole's gravitational pull is no stronger than the object that formed it. The event horizon does not change this. It is not a mouth. It is not a vacuum cleaner. And it does not spread outward through space. The event horizon is simply a boundary very close to the black hole itself. Unless you come extremely near it, it has no special effect. This is another point where imagination often runs ahead of reality. Most black holes are quiet. They sit in space doing almost nothing at all. They do not glow. They do not roar. They do not disturb their surroundings unless something wanders very close. Even then, they do not behave violently. They behave predictably. The black holes we know about are also very far away. The nearest known black holes are thousands of light years from Earth. Between here and there is an enormous amount of empty space, space that is calm, stable, and safe. Nothing about black holes suggests they pose a threat to everyday life. They are not cosmic disasters waiting to happen. They are natural outcomes of well-understood physical processes. In fact, black holes are among the most orderly objects in the universe. They obey strict rules. They follow precise geometry. They respond to gravity in consistent ways. The fear surrounding them does not come from what they are. It comes from how they are often described. When language becomes dramatic, our instincts fill in the rest. But when we slow down and follow the physics carefully, the picture becomes much calmer. Black holes are not agents. They do not act with intent. They do not single anything out. They simply exist. And they exist very far away, very quietly as part of a universe that is far larger and far more stable than fear usually suggests. Understanding this is not just comforting, it is grounding. It brings us back from the edge of extremes to a clear perspective. Black holes mark the limits of theory, not the limits of safety. And with that understanding, we can finally relax our grip on fear and look at the universe as it really is. Vast, structured, and remarkably calm. We've come a long way together. From the quiet life and death of massive stars, to the formation of event horizons, to questions about information, time, and the limits of physics itself. We've followed gravity to its extremes and watched the universe reveal how patient it can be. Now it's time to slow down, to step back, and to remember where we are. Here on a small planet, orbiting an ordinary star, moving gently through a galaxy filled with light, dust, and long silence. Black holes still exist. They always have. They rest in distant regions of space, embedded in galaxies far beyond our everyday concerns. They are not moving toward us. They are not watching. They are not waiting. They simply are. The universe continues to operate according to its rules, quietly, consistently, without urgency. Stars will continue to burn. Galaxies will continue to drift. Black holes will continue their slow, patient evolution. And none of this requires your attention right now. We are small, yes, but we are not fragile. The same laws that allow stars to collapse also allow planets to remain stable and nights to pass without disturbance. The same physics that bends space-time also keeps Earth turning steadily beneath your feet. As you rest, the planet rotates at a calm, familiar pace. Above you, the sky remains wide and unchanged. Far beyond that sky, black holes sit quietly, doing nothing dramatic at all. There is nothing chasing us, nothing hidden nearby, nothing unresolved that needs an answer tonight. Some questions in physics remain open. That is a sign of progress, not danger. It means the universe still has depth, still has layers, still invites curiosity, but never demands fear. For now, the journey can pause. You do not need to follow every equation. You do not need to resolve every paradox. The universe will keep going, patient and steady, whether you are watching or not. So let your thoughts slow. Let the questions fade into the background. You have explored enough for one night. The cosmos is vast, it is calm, and it is in no hurry. And you, right here, right now, are exactly where you belong.